In this video, we want to look at chemical equilibrium, and if, for example, we have A reacting with B and produces, when the forward reaction equals backward reaction, it produces C D. Now, if the forward reaction equals backward reaction, then equilibrium is reached. That is why equilibrium can be said to be reached in a system when the rate of conversion of reactants into products equals that of the conversion of the product back into the reactants. If, for example, we have hydrogen reacting with iodine and they are in equilibrium, then it will produce hydrogen iodide. Another example is we can have NO2 reacting with CO being in equilibrium to produce NO plus CO2. It always uses the law of mass action, which states that when equilibrium is attained in a reversible reaction at any given temperature, the ratio of the products of the molar concentration is divided by the ratio of reactants with respect to their molar concentration raised to the power, that is the number of the mole present in the species. What we mean by that is that equilibrium constant, we use K to denote it, is equal to, in this case, that the concentration of the products, concentration, this is parenthesis, we don't use brackets. Bracket is not used, they don't mean the same. So parenthesis signifies concentration of the products raised to the power, the number of moles here is small letter c. Let's rewrite it. K equal to concentration of C raised to the power small letter c, then multiply by the concentration of D raised to the power the number of moles divided by A, concentration of A raised to the power small a, concentration of B raised to the power small b. So now let's write the equilibrium constant for this reaction. We're going to have that K will be equal to the concentration of hydrogen iodide raised to the power the number of moles, which is 2, divided by the concentration of hydrogen multiplied by the concentration of iodine. That's it. Now for this reaction, feel free to write the equilibrium constant. Pause the video and write. We can have that K is equal to concentration of NO plus concentration of CO2 all over concentration of NO2 times concentration of CO. One major thing also that we need to note is that the equilibrium constant of solids are not written. If, for example, we have this reaction and we are asked to get the equilibrium constant, you will notice that solid is involved. If we are to write it now, we start with the product. We don't write this. So K will be equal to, we'll pick only this, concentration of hydrogen raised to the power 4 over here, we don't write this, we'll write only this, concentration of water raised to the power 4. So let's solve this question. The equilibrium constant at 200 degrees Celsius for the reaction this is 4.1 times 10 raised to power minus 4. Calculate the equilibrium constant of NO if the equilibrium concentration of nitrogen is 0.036 mole per liter and oxygen is 0.0089 mole per liter. Let's begin by bringing out the parameters. The equilibrium constant is K equal to 4.1 times 10 raised to power minus 4 mole per then for that of N2 is 0.036 mole per liter. Then that of oxygen is 0.0089 mole per liter. So let's write the equilibrium constant of the reaction. It will be K equal to concentration of the product all squared, which is all squared, then divided by that of the reactants, the concentration of N2 and the concentration of O2. Let's fix these values into here. It will be K is 4.1 times 10 raised to power minus 4 equal to concentration of NO squared over that of these two, which is 0.036 times 10 raised to power times 0.0089. So we have 4.1 times 10 raised to power minus 4 equal to concentration of NO 0. When we multiply this and this, we're going to get 3.204 times 10 raised to power minus 4. So make this subject of the formula. We have NO equal to this times this gives us 1.314 times 10 raised to power minus 7. Therefore, only the concentration of NO becomes the square root of this value, 1.314 times 10 raised to power minus 7, which is equal to 3.624 times 10 raised to power minus 4 mole per liter.